Now, we're going to look into the future. I absolutely love the title of this panel. Is it up there yet? Quantum computing, far away, around the corner, or maybe both at the same time. It's just exactly what we need to talk about now. Our moderator is the director of the Berkeley Quantum Computation Center and UC Berkeley professor Umesh Vazirani. Umesh, please bring your panel up to the stage. Thank you.
Good morning. Welcome everybody to this panel. It's great to see so many people here early on Saturday morning. So let me try to lay, set a little bit of the background for this panel. So back in 2014, Google decided to get into quantum computing in a fairly major way. They actually hired John Martinez there, and then, more recently, Microsoft announced a move from pure research to building working prototypes of quantum computers late last year. And then early this year, IBM announced that it was going to be an industry-first initiative to build commercially available quantum computing systems via the cloud. Now, this is in parallel with a large number of startups that have happened recently in quantum computing: IonQ, Quantum Circuits, and Rigetti, to name just a few. In the meantime, Europe announced a €1 billion project in quantum computing. So that's all maybe around the corner. In the January issue of Nature, Dave Wineland, who got the Nobel Prize in Physics for his work on ion-trap quantum computers in part, said, I'm optimistic in the long term, but what long term means, I do not know. Okay, so in this panel, we'll try to peel back some of the covers and look at some of the questions here. I'm sure everybody here knows that quantum computers allow you to, allow for quantum speedups on computational problems. And I'm sure almost everybody here knows that this is not for all problems, right? That computational problems have to have certain properties for them to get these exponential speedups. And that's a very, and in fact, there are known limits. So we can prove that certain problems won't be speeded up. There are also other challenges that are unique to, well, that take on a very, that take on a unique flavor when they are viewed in the context of quantum computing. So error correction and fault tolerance play a very important role, a much more important role once we go to quantum computing. But then we also have, so moving forward, besides the question of actually building the hardware, which is a huge challenge, there are also other critical challenges in algorithms, and then other uniquely quantum challenges, such as how do you even test such systems? Okay, so hopefully we'll talk about all this, but also about the fact that quantum computing provides a new language in which to talk about quantum mechanics, and there are some very exciting developments which I hope some of the panel will actually describe. So let me just these are a lot of topics to talk about in the time available. So, but luckily we have a very distinguished panel. So let me introduce them. I guess in the order that they are seated, Dorit Aharonov. She already laid the foundations of fault-tolerant quantum computing in her dissertation. She's worked on, so Dorit is a professor at the Hebrew University, and she's worked on many fundamental aspects of quantum computing from a theoretical viewpoint, including pioneering work on testing quantum computers and quantum mechanics. Next to her is Jay Gambetta from IBM. Jay works on quantum validation, on quantum codes and coherence and near-time applications of quantum computing. He leads a group that works on this at IBM, and for his work on all this, he was named the 2014 Fellow of the American Physical Society. Andrew Yao, I guess he got, of course, the Turing Award for his for laying the foundations of complexity theoretic cryptography and pseudorandom generators. But what many of you probably don't know is that before he got his PhD in computer science, in 1972, he got a PhD in physics from Harvard with the Nobel laureate Sheldon Glashow. And Andy has done actually foundational work on quantum computing, starting with his work on universal quantum circuits, as well as his work on setting sort of setting some of the framework for within which we should test devices for quantum cryptography. So that framework is called device independence. And John Martinez, who I already mentioned, he's been working for a long time on superconducting qubits and more generally on low temperature device physics. He's been working on superconducting qubits for quantum computing since the late 90s, but in the last decade, he's really made stunning advances in superconducting qubits, culminating in, he used to be at UC Santa Barbara, and where he implemented surface codes on using superconducting qubits, work for which he was given the London Prize in 2014. And then, as I said, in 2014, he was spirited away to Google, and he's working on a very ambitious project there. The way we'll structure the panel is, every panelist will now speak for 5 minutes about their thoughts about this topic and their relation to this field, and then we'll have free-form questions, followed by questions from the audience. So, please.
Okay, hi, my name is John Martinez. I guess I'll go first. I have a great job. I'm trying to build a quantum computer. I really enjoy that. It's an exciting time because I think we're going to start putting together really interesting systems and powerful systems. And we're all used to CPUs and GPUs and now TPUs, and soon we'll be working on QPUs and hopefully programming them and doing interesting things with them. There's a lot of discussion. I liked the discussion even yesterday on quantum computing. And I think this kind of crowd, there's this expectation that, okay, this hardware is just going to get built and we're going to have a quantum computer. I want to caution you that maybe it's a little bit harder than you think to build this thing. And I think partly you're really spoiled by CMOS, because CMOS works so well and has made such a big thing. I'm going to say, just going deeper on that, is what we have to do is we have to develop essentially a new engineering discipline I mean, we all know systems engineering is important, but I'm going to call it quantum systems engineering, because these machines have to be put together in a little bit different way. And if you kind of rely on your classical intuition on how to build these things, so maybe it'll be a little bit harder than that. And I'll just give you an example. In quantum information, you cannot copy information. And think about how you're going to build a quantum computer when you can't copy information. So you can't use necessarily a simple data bus. Your data storage is going to be different. And you know, that kind of thing just permeates into all the design, and I think makes it hard. I mean, I think it's fundamentally possible to do it, but it just makes it hard. And we'll be seeing, as people are trying to build complex systems, kind of how this all plays out. I think it's a very interesting time because of that. The other thing, there's lots of different proposals out there for building hardware. And okay, let's say there's a little bit of hype going on. We all understand that. I kind of took the title of the symposium to heart and said that as I think about whether things, what's going and what are the right approaches, whatever, I kind of use my quantum mindset and think about all these different approaches in my mind as a superposition of these ideas working and not working at the same time, okay? I don't know a priori what's gonna happen, okay? But the important thing is, if you want to know, like in quantum mechanics, we have to do a measurement, okay? In this case, the measurement is building the ideas and the hardware and seeing if it works. And I think only by looking at the data and seeing what ideas work and what ideas don't work, that we're gonna know, you know, which of these ideas are really gonna fundamentally work. Maybe they'll all be good, and that's great. But, you know, it has to be very much empirically based, I believe. And I think the audience here is kind of used to that. So we just have to do it even more so with quantum. I'm going to talk a little bit about what we're trying to do, and I was very pleased yesterday someone mentioned quantum supremacy. That's something that's very much on our hearts and minds, and we're pushing forward to do that. The basic idea is to make about a 45 to 50 qubit device, and what's really important is make those qubits with low errors. Something like 1 error in 1,000 operations, or few errors in 1,000 operations has to be done. And that's really hard, especially as you're scaling up. That's the big challenge. And then the idea here is we run a very simple algorithm and get output, and then we check the output. We have to check the output by running a classical simulation of the quantum mechanics on a supercomputer, and you have to use a supercomputer because the state space of this is 2 to the 45 or 50th, a huge number, and only can a supercomputer deal with that. And you know, by doing that, we can hopefully you know, show these things. So I think I've really seen that as we propose the quantum supremacy, I see the computer science community kind of understanding and appreciating this really well. And I like that. And I kind of want to highlight 3 areas where I think this is going to be really interesting to do this experiment. Is first of all, kind of on a basic science, is the whole point of a quantum computer is to have this exponential speed up where the amount of computation power you're doing goes as 2 to the number of qubits. And the quantum supremacy really demonstrates that you can do that to a scale that is going to be really interesting and useful. And we like that we can directly, if we're going to spend all this time and money building this thing, we want to know if it's going to work to some big degree as soon as possible. The second reason I'm doing this is kind of a managerial reason for me, in that this experiment really focuses our team very well. Not just on making a lot of qubits, but we have to make them well. We have to have low errors. And doing these 2 things at the same time is really hard. So by having a good experiment like this, the team really understands we have to do the system engineering to get it right. And I'm going to say if we can do this, the supremacy, what's nice is it kind of means you can do error correction. Maybe you have to do more things, a little bit harder, but it gets most of the way there to doing it. So it's an extremely good stepping stone, very concrete project that we can do. And finally, I want to share something that's a little bit of a wild idea, but I think people in this audience will really appreciate it. And that is, if we can get the quantum supremacy experiment to work and have something as powerful or more powerful than a classical computer, we're only one algorithm away. It's a clever algorithm, that's for sure, but one algorithm away of doing something useful with it. And we're hoping, okay, it's really hard. I'm not saying that we can do it, but if we have the hardware there and it's out there, then it's going to motivate people, like in this room, to think about this. And all these different thoughts might actually push us forward in doing that. So to kind of encourage that, we want to take our machine and test it in-house, but also make it available to outside people, like what IBM has done, and D-Wave has done, and make it available and then see if people can think of it. Because, you know, clearly you've seen that in your world, that having a lot of people thinking about these fundamental ideas is really good. So finally, just what's the progress on it? We've had a 9-qubit device. We took data in January. We talked about it publicly in March. The paper's been submitted on 9 qubits, where we demonstrate the supremacy algorithm. We know it works. We know how to take data. That's good. And the state space that we're computing there is about 500. So it's big, but we need to make it bigger. Right now, we have a 22-qubit device that's made and in test in our dilution refrigerator, and things are looking good. And in fact, in the last 3 months, or last 1 month, we've kind of fixed 3 kind of remaining problems that we had to work on to do the supremacy experiment. So we're implementing and whatever, but this is looking really good. And you know, the supremacy chip is in design right now, and we really think we have a good chance of at least trying it out this year. Okay, that's on our timeline. We'll have to, of course, see if it works. Thank you.
I'm Andy Yao, and I am a believer in quantum computing, and so I'm really pleased to hear that John had a very optimistic note on the prospect of quantum computing. And actually, just in the last 6 years, I noticed that there has been a tremendous progress, both scientifically and also in the public reception of the idea of quantum computing. And it stuck in my mind because I remember in 2011, I was invited by John Hopcroft to give a talk in a computer science frontier type of symposium. And the title of my talk was Quantum Computing, a Great Science in the Making. And after I sent out the title to John, I got a queasy feeling because the audience was going to be essentially a purely computer science community. So I thought I was perhaps a little bit too aggressive in pushing this line at that time. And the saving grace is that after I arrived there, I ran into Alfred Aho, who is a computer scientist at Columbia University. And he said that, what are you going to talk about? He said that he was going to talk about quantum computer compiler. And so at that time, I felt a great relief because whatever needs defending, I think Al was going to do it for me at that point. And now, just in a short 6 years, I think right now that we all feel that quantum computing it's going to have a bright future, not only in the sense that it's a great scientific endeavor, because it really is the first time since the Alan Turing's work that the computing machine has acquired a really fundamental different ways of operating. So the scientific value is very important to us, computer scientists. But also, it really seems that clear that the technology of quantum computer is going to have some very big practical impact in the future. So now, on that note, I would like to touch on 3 points. The first one is the benchmark question, is that how are we going to judge that we have achieved what we want? And I think John actually put it very nicely to it. It's, it really seems that people are working with different technology and trying to build different type of quantum computing devices. So I think that right now, I think it'd be very nice if somebody can come up with some set of really good criteria that we can all think it's something that's a good landmark for it. And just a few days ago, I was in a computer science conference, and a prominent theoretical computer scientist came to me and asked that when do you think we'll have a quantum computer that can actually factor 1,000-digit integers? And so that's a benchmark question, and I thought that is a very typical computer scientist mindset because we are used to the clarity. And, but I think that benchmark also would be something that's almost impossible to attain, I think that in the foreseeable future. So I think the physicists get it more right in that actually the attitude in quantum computing should be one of sort of, it's a great experiment, and we are all waiting to see what can come out of it. It's an unknown adventure, and actually, in my mind, that makes it a really great scientific saga, because if it were a purely engineering problem, then it wouldn't be really exciting at all. And the second point I like to touch upon is what is the role of computer scientists in this endeavor? Because I think right now, I think all people talk about, and if you read the public press, really it's essentially it's a game for the physicists. The race to build scalable, great quantum computing devices really is in the laboratory of the physicists. So what do computer scientists, what's our role in it? Actually, I think quantum computing is a very great paradigm for the interdisciplinary activities. Computer scientists have made great contribution in the early days of getting this field started. In particular, the demonstration of the ability to factor integers by quantum computers has lots to do with getting attention for the various agencies to get the projects started. So right now, it seems that all the attention is in making the hardware, but actually there's a lot of intellectual effort computer scientists can do to prepare for the future. For example, I think the Aharonov quantum compiler project, the idea of building quantum software, actually right now, I think Umesh mentioned it at the very beginning that there are many big companies like IBM, Intel, and they are very interested in the idea of building quantum software to prepare for the day when quantum computing becomes a reality. And also, I think that somewhat under the shadow of the hardware, there are still a lot of very interesting activities going on in research between quantum physicists and computer scientists. And there's I think there's a very good interaction between these two communities. Let me just give you an example that some paper by Umesh and his colleagues a few years ago have designed algorithms to find low energy states in quantum models. And actually, this line of work is now actually starting to have an impact in the mainstream physics work. And on the other side, there are some very innovative ideas from people like Seth Lloyd, and they are talking about quantum big data and quantum machine learning, quantum neural network. And actually, if you look at it, there are some really interesting ideas in it. For example, the idea of quantum big data is that the quantum mechanics, in principle, gives us the potential to be able to compress a large amount of data into logarithmic space. And now, of course, the law of quantum mechanics makes it impossible that you will be able to store and retrieve at will this amount of data. However, it is possible to operate, to do manipulations in this compressed form. And hopefully, for some type of problems, like doing linear algebra type operations, it's possible to obtain results just working in this reduced representation. And that's the idea of the quantum big data. And so, of course, all this really can become really useful only when the quantum computers becomes in a usable form. And now, the last point I want to touch upon is more general in nature, namely that I think this is a very good time to reflect on what computer science has achieved and what is in the future for us. It seems that in the past many years, especially in the early days, computer science is more involved, more inward-looking. We are trying to build computers and manipulate them in the most efficient way possible so that they become available for many other disciplines and for the societal use. And now, however, in recent times, I have had the opportunity to participate in many committees involving scientists from different disciplines to evaluate things like to give prestigious fellowship to scientists, irrespective of their special fields. And there I felt very acutely that it seems that the world of science has moved outward to an open stage where achievements in different fields between computer science, mathematics, physics, chemistry, or biology, they all somehow have the opportunity to be viewed on the common platform, so to make judgment. And so this means that perhaps in the future that the way for young scientists in computer science to progress is not just that to go to your very specialized conferences and impress the elders in that discipline, but actually it will be judged not just by how important it is to your subfield, but actually what kind of impact that you have. And I think that the quantum computing is a particular area where we really should start paying attention to it. And when I think about the reception of the computer science departments to quantum computing, it's less than satisfactory. I recall that 15 years ago, around the year 2000, and now if you look at what computer science departments have people working in quantum computing, and I can count maybe 4 or 5 computer science department with scientists, computer scientists in it. And now, 15 years later, if I look at the US computer science departments and how many departments have specialty in quantum computing, and I think there are maybe 7 or 8. So I think it's a very small number of quantum computer scientists that I think that will be missing the boat, because the quantum technology is, in my mind, the rightful successor to the microelectronics revolution. And I think computer scientists shouldn't miss the boat, and we should nurture our scientists, and the computer science department should be more open to the idea of hiring computer scientists in this endeavor. So that's what I want to say.
You want to go next? I don't mind. It's up to you. Okay. All right. Yeah, so my name's Jay Gambetta. I'm at IBM. We've been looking at quantum computing for a very long time. It actually started originally with Charlie Bennett and Rolf Landau asking a question about, is there a fundamental relationship between information and physics? And they went through and did a lot with reversible, and a lot of quantum information was done there. I hear a lot of people say, like, quantum is faster, it's gonna replace things. I actually don't like this view, and yesterday, listening to some of the panels and people talking about us building specially built hardware, quantum is a sort of like that. It's gonna be something specially built, but it's not gonna be that it's faster, it's gonna be that it does something different. And to everyone, I advise, don't try and make an analogy to anything you do classically. It uses entanglement in that. So long term, I agree with what Umesh had at the start. We want to get towards doing what's called in the community universal fault-tolerant quantum computing. This is coming up a way, with the words what that says, as doing the computation even in the presence of errors. This is still a long way out. Why is there interest, or how around the corner and how those come in and now? Well, I think we're going through a change in sort of quantum computing. When I started as a student, and many of these people up here were either founders and experts in the field, either bringing and understanding the concepts of fault tolerance, quantum complexity, and things like that, coming up with superconducting qubits and how they did, it was almost like two independent fields. They had the people that were working on what will quantum do, what will it do in the presence of an ideal world, and people working out how to build it. And I wanted to learn both, and I think what's really exciting now is we're at the stage where these two are coming together with more and larger experiments that are beginning done, with things like last year when we put our quantum computer on the cloud. We had to come up with a way in which we could abstract away the superconducting physics, abstract away microwave engineering, and start to build for the first time some set of minimum instructions that you could use, that you didn't have to understand exactly what the physics were. We called this open QUASM, and there's been various other proposals throughout the history of quantum research, but we put this on Git and we made it available to people to start to actually go and program. One of the most exciting parts about that project for me is there has been 19 papers by people that are not us using our hardware. So people have come and they're starting to use it and do things. And we're now working to the stage of saying, rather than just give you this sort of like assembly-like language, and that's why we called it QUASM, how do you start to work towards a programming language? Not a programming language with fault tolerance in mind, because that's still a fair way away. So we've started to come up with ways in which you can batch jobs together, submit them, and then run them. So it's kind of like 3-stage. You build your algorithm that you want to do, you submit it through the cloud to execute it, and then you compile it to get it to an outcome. And in a lot of these sort of near-term applications, they're going to require sort of running lots of things and combining them together to look at things. So I see with my group, one thing I like about it is we have engineers, we have physicists, we have computer scientists, we have mathematicians, and we have them all together. And we're starting to really try and understand this and put a lot of those concepts together. What I think is emerging is I like to call, without a better name, a sort of model of computation what I want to call universal approximate quantum computing. Because we're trying to ask, is there any value in something that is beyond what we can simulate, but turn it around to do something of practical advantage? Some of the things that we do in this is just actually looking at small codes. A lot of these codes were designed in the absence of knowing what the errors are in real systems. So as we make smaller codes and look at different types of codes and follow different codes to look at whether the noise is correlated or has some type of feature, can we adapt our codes around that? Other areas is, as mentioned, is trying to prove that there's a separation between classical and quantum. I don't believe there's going to be one step. There's going to be accumulated evidence by the community. We trying to come up with ideas in our group, not myself, but people that I work with, of restricting the classical algorithm and the quantum in some way, and then to prove an advantage. And we're trying to formulate those ideas so we have an accumulated set of evidence that our systems will eventually be better than classical. The third is just look at heuristic algorithms. Sometimes it's hard to prove algorithms. It's actually really hard to prove algorithms in the presence of noise. So as we build this hardware and we work harder to make this hardware bigger, what can we do on it in a way that is based on some clever idea? And the ways that we've recently done is looked at this variational quantum eigensolver, which essentially treats the quantum computer as like a processor that you put with some classical algorithm, you repeatedly call to it and minimize until you find the eigenvalues of some Hamiltonian. I'm not going to say in any way we can prove that it scales better, but we just want to try these on hardware, learn for different trial states, which ones work, and learn from actually working with real hardware. Are there things and areas we can look at? And the third is what has been mentioned. How do you verify that the system is truly becoming quantum? There are it's very hard to simulate. Like, there's two things that make quantum computers hard. It's hard to simulate because it takes a lot of RAM to represent it on a classical computer, or if you've got a very long program, you have to transverse many paths to simulate it. And so putting these all together and working out, when I have systems, how do I prove something as quantum is an active area that we do. And we do all this under this sort of place of what we call approximate quantum computing, where we're trying to actually learn and get this gap between the path to get the fault tolerance. I like to think of it as kind of the exciting times that I assumed the digital computing went through. We're trying a lot of things. I don't know which ones will work out. But what we're trying to do is putting most of the stuff that we build online, making it open source, giving people the ability to come use it and build upon it, and then work with the community. And that's all.
I'm Dorit Aharonov from the Hebrew University. And following up on what Jay was talking about, so probably we're all, I mean, if you're in this room, you're asking yourself, maybe, what actually makes quantum computation so interesting now? I mean, Shor's algorithm is here for already 23 years. And why is it that there is such an explosion over the past few years in the interest in quantum computation? And I think one way to explain it is that, in fact, there's not just one era of quantum computation, but there has been two revolutions in quantum computation. The first revolution was that we realized, as a community, that quantum computers can solve certain problems exponentially faster. And then for about 10 years, the scientific community was concentrating in two separate paths. The computer scientists doing quantum computation were concentrating on trying to find algorithms that are exponentially faster, other algorithms than Shor's algorithm and its descendants. And then the physicists were trying to come up with a quantum computer that will realize those algorithms. But then at some point, at least from the computer science side of things, people just realized, well, this is a really, really difficult task, coming up with new quantum algorithms that are completely different. And they got fed up with this. And then they started to think what else can be done with quantum computers and with this whole new thinking about quantum systems. And what happened then was, in fact, a new revolution, which can be, I think, traced back to something like 2005 or something like that, where computer scientists started to see the whole language developed in quantum computation as a way to investigate physical systems from an information theoretical point of view. And then that led basically to the question of what is different in a quantum system that I can see if I just look at it as an information processing device. And together with that came this question of what else can we do with quantum systems experimentally if we look at these systems from an information processing point of view. And that is tightly connected to this question of what can be done now with quantum systems in the near future, and not trying to build a full quantum computer. That effort is of course continuing, and we are seeing very beautiful progress. But on to its side, started to emerge really beautiful applications of looking at physical systems as small information processing devices, just from understanding that quantum processing is different than classical information processing. And I want to give one particular very beautiful example, and this is related to precision measurements. So this whole area was sort of not touched by quantum computer scientists before, but there are several contributions coming from this penetration of computer science ideas into this question, which is entirely physics. And one such example is quantum error correction, which turns out to be helpful when you're trying to measure a certain physical system and, say, estimate a parameter, and but this physical system decoheres, or its quality gets degraded as time goes by during the measurement. And then if you're using quantum error correction during that measurement, then the system is, you will be able to measure it for a longer time, and you will be able to get more accurate results. So this is an idea that it's small scale, and yet it comes from the language, the new language that has developed in computer science of quantum error correction codes, and it was borrowed into questions such as, can we do better precision measurements? And there are other ideas like that. For example, can we use entanglement that entanglement between different probes to gain more accuracy? There are also other ideas like that from theoretical computer science, like reductions between different physical systems that have penetrated physics, and that also enable using using sort of completely theoretical computer science ideas to do new physics, and in small scale rather than in large scale. And I think, in my mind, this is it's a really exciting revolution. You can view it as a computational physics revolution, in which quantum physics is now treated as an information processing, from an information processing point of view. And I think one particularly very interesting question or challenge is that, well, whereas we know the challenge of developing quantum algorithms, and we have the language for that, we don't yet have a theory for developing quantum measurements or quantum experiments, a theory that comes from theoretical computer science. And I think such a theory is now at the point of getting developed, and we're only starting to see it. Thanks.
So I wanted to pick up on two things. One thing that Jay and Dorit talked about, which deals with this notion of quantum error correction and fault tolerance, and these two kinds of, so, well, going back to this superposition of around the corner or far away, perhaps this, one reason this superposition exists is because of the goal that people have in mind. So one goal we might have in mind is doing large-scale quantum computing on perfect qubits, where the point is that if you have n qubits, there's an associated Hilbert space which is exponentially large in n, and this is a perfect Hilbert space because these were perfect qubits. But if you actually build a quantum computer, you end up with noisy qubits, where you can drive the noise down, as John said, to 1 in 1,000 or smaller, but it's still noisy. And so you can either think about how to compute with those noisy qubits in the short run, or you can think about how to do error correction, and then you need many more qubits. So, there's a question, well, what, in terms of the path to quantum, to useful quantum computers, what is this going to look like in terms of these two different sort of directions to go with? Yes.
Sure. So I don't think they're fundamentally different. I think part of what you want to do, you want to get to fault tolerance and you want to get to error correction, but you're building, the most important thing at the moment is to build devices that are larger and larger with good fidelity and lower errors and connectivity. So what we tried to do is, we came up with a metric that we want to follow for our hardware, which is basically, we call it a quantum volume. It's related to how good our gates are and how many gates we can do. And then within that framework, I think you can start to look at codes. You can have your codes that you may prefer up front, like a surface code, but you can start to ask questions about the errors and feed that back to computer scientists to develop better models. So I think that going through the path that we want to take, fault tolerance is up here. We know perfect theory for how it will work under certain codes, but these codes that exist at the moment have a pretty large overhead, so we want to build the hardware and follow that. But I think at the same time, with that same hardware, you can test other things that are doing it within precision, like heuristics and things like this. And we actually also think that you can do things like, we term it error mitigation. So if my goal is just to measure observable, I can resample to get that observable a better fidelity within a short amount of time. So there are other tricks that you can do that are not error correction to make the thing that you do in the near term have better fidelity, and that's what we're looking at as well.
So would it be fair to say that the difference between people who feel that it's far away versus close by, around the corner, is how useful they think noisy qubits would be? That error-corrected qubits we'll call logical qubits, the perfect qubits. So how useful are physical qubits versus logical qubits? Is that the difference?
Yeah, and I was going to concur with what Jay's just said and maybe explain it in a different way. If you look at digital computing right now, at the beginning of electronics, digital computers were very hard or complex or expensive, and people made analog computers out of electronics, and a lot of interesting problems were solved in that way. And then it's only because digital computers became so incredibly performant that all the analog computers went away. So now we're at the beginning of quantum information. We're kind of thinking of this non-error corrected applications as building analog systems, okay? And build them so it's tolerant with noise, and if we can do that. We don't know if we can do that. So that's what we're trying to do. So we have experiments on 3 different hardware types. We're looking at the annealer. We're looking at kind of the circuit model of discrete gates, and also kind of a circuit model with continuous gates. And we think all 3 of those are really interesting ideas, and we want to see which of those will be interesting from this analog sense. And then, of course, the nice thing is, as Jay said, is as you build these systems better and better, you're learning how to do them so that you can do fault tolerance, and then we will eventually get to the digital quantum computer, which, of course, we expect to be better in all sense and be able to run more algorithms. So I think the field may evolve in this way, in a nice way. We'll just have to see whether we can solve practical problems. That's really an open question, and we're hoping that a lot of people will be looking at the heuristic kind of algorithms, as Jay talked about, to see if that's possible.
Can I follow up?
Yes, please.
I just want to say back to what Dorit was saying as well. I think what's most exciting for me is I think the computer scientists will start to come to those and say, what can I do with not fully corrected? And it's very hard to prove, but if you can start to actually then design these on these systems as they get, I think that's the exciting part for me.
Yeah, so just to say it in a different way, if you look at the kinds of machine learning algorithms that are proved and analyzed, that's a very small number of algorithms, whereas the number of algorithms that are deployed out there, which work well in practice, that's a much larger class of algorithms, and so, you know, this question about how do we develop quantum heuristics is something we haven't, you know, we've been thinking about only for a few years, and this is something where there's a real need to focus.
Yeah, and we're just going to say that with IBM Quantum Experience and of course Google, we would like to do this too. If we have machines out there, then it will be easier to approach these problems and use them, and I think students and other people will be more interested. So we think on the hardware side, we have a lot to do to encourage this too, and it'll be exciting to see what happens.
So John, may I ask a naive question? So, you know, as somebody who is a theorist and has no idea about the difficulty of building hardware, shouldn't the task of building a 300-qubit quantum computer be just 10 times as hard as building a 30-qubit quantum? What's taking so long?
So yeah, we had 9 qubits at UC Santa Barbara, let's say 3 years ago, and you know, we've doubled that in 3 years. So what we've been doing is building up all the infrastructure so that it's scalable, okay? When we did at UC Santa Barbara, you know, this is graduate student written code, which is actually good students, but it was kind of breaking, okay? Because things were not done in a way, and that's rightfully so. That's how you would do it. Yeah. So what we've been essentially doing for 3 years is getting all our infrastructure in line. And I'm going to say, working at Google, we're now all very good coders, okay? And we use standard industry practice for coding so that everything is working better. And then we've had to do that with all the hardware. So we think we've had that figured out. I mean, obviously we didn't put it together, things will break and we'll have to fix them. But we do that, and we think with that figured out, we're now in kind of a scaling regime where, you know, if we're lucky, we can do a little kind of Moore's Law thing for a few generations and scale up because we have things under control. And so, you know, but that's taken, let's say, 3 years to get everything in control, and now we're going to hopefully do that. So, you know, the supremacy chip, we hope to be kind of the start of what will be an interesting line of chips coming from us. But, you know, again, we'll have to see.
Yeah, so I agree with a lot of what John is saying. For a long time in the field, John and I have been working with John much longer than me in this field. It was really 1 and 2 qubit experiments. And one of the exciting parts is now we're starting to be able to start to put multiple together. We have similar rates that John is. But you also have to do at the same time, if I was to build 300 qubits and the fidelity of the gates did not go up, you can't explore much of that space. So there's still a lot of significant work to be done to lower the error rates, improve the coherence. So you've got to keep building these fundamental concepts and keep pushing that up to make these larger devices useful. Because if your primitive is only local interactions, it takes a long time to build up these more complicated things. And so I think and that's one of the reasons why it's around the corner, is you definitely are seeing a trend of putting more of them together in a way that starts to look like it's going to start tiling out. We've just put 16 online, and they're of the same order as the 5.
So would you say that one of the concerns here is that until you get to a fault tolerance threshold, that as you increase the number of qubits, you also have to improve their quality a lot. And so it doesn't increase linearly until you get to that point. And that once you get to that point, would you say that then doubling the number of qubits would be relatively an easier job because you can now stop improving the physical quality of the qubits and let the software do the work?
What kind of happens is, as we've been figuring out how to scale up, we have to make all our engineering practices better. And that actually helps you with the quality and the noise and other things you do. So that's kind of one of the reasons we pause to make everything better. So I think for a while, this is going to kind of go together. Hopefully this year, next year, we'll figure that out. But moving beyond that, we're just going to have to see. I mean, we have to take data and see what's wrong and, slowly figure it out. And we definitely have to work on both. That's a big message here.
So, sorry.
Yeah, well, let me take advantage that we have the hardware experts here to ask the question that I understand that I think both IBM and Google, you are working with superconducting storage. And now there are other quantum computing material technology also. So can you comment on are there any competitions inside, say, the ion trap or the diamond and the semiconductor, the other type of technology? I mean, why do you focus on superconducting, and what are the prospects of the other can they do the same thing that you do?
Well, yeah. So as a hardware person, you have all this experimental infrastructure to deal with. So you tend to just focus on one particular technology set, and it would be hard to do something else. We like superconductors, and ion traps were considered for years and years as the leaders, and I think superconductors have come on its own right now, and maybe we're leading. People might argue that, but superconductors are great because we can scale using IC fabrication, and things are working very well. Ion traps have really good coherence and good gates. But the scaling is a little bit harder, and I'm going to say, well, for part of the reason is that people have to learn how to make ion trap chips and get those to work well, and that's kind of a longer learning curve. We're focusing on that because that's just kind of what's working for our thing. We're keeping an eye on other technologies. And I'm going to say that I think if something else was to become really compelling, we would think about pivoting and doing that or doing that too. But we have the basis on data. And certainly people are making rapid progress, say, in ion traps, and we're doing that. And then Microsoft's with the topological qubits is something we're also looking at very carefully. If they can get that to work, then it's a really interesting system. And then we have to decide what to do.
Thank you.
So I want to come back to something Dorit said about this new way of thinking of quantum systems as information processing systems and from a computer science viewpoint. So I want to come back to that with this notion of that one of the challenges moving ahead will be testing these quantum devices and quantum computers. And can you speak to something about this?
So over the past few years, there's been what I think is a very interesting development, which is it's the understanding that, in fact, the very basis of the whole theory of quantum computation tells us that, in some sense, in the usual scientific paradigm, what's a usual scientific experiment? You have a theoretician, you have an experimentalist. The theoretician sort of conducts an experiment and computes what is supposed to be coming out of this experiment at the end if we measure. The experimentalist runs the experiment, and then they compare and see if the experiment matches the theory. But one part of this whole picture, so there are two parts, the experimentalist and the theoretician. The part of the theoretician assumes that the theoretician can compute the prediction. But this prediction is very hard to compute if it's a prediction, if we're going to predict what a quantum system evolving according to the laws of quantum mechanics is going to do. That's the whole reason why quantum computers are interesting. It's because it's hard to predict, right? So that's why quantum algorithms are interesting. But on the other hand, we don't know how to make the prediction of a quantum experiment. So this is a very interesting understanding that the usual scientific paradigm will not work if we want to test quantum systems in sort of the high complexity regime where it's doing something that cannot be done classically. So then, over the past few years, there's been a lot of progress in understanding that, in fact, if we bring the idea coming from theoretical computer science of instead of thinking of the experimental system as something that we just initiate, press a button, and then run, we can probe it in a structured way. We can sort of run an experiment and then get an answer, and then from the answer we, in a structured way, adapt the experiment. So you can do an interactive experiment in a structured way. Then, in fact, it is possible to test quantum mechanical systems. And we now know that in various settings, one can do these interactive experiments, and it's still, I mean, mostly it's theoretical. There has been some interesting experiments attempting to do that. But I think this is a very interesting paradigm that we are still really not understanding. We at this point, we are sort of at the era of the first 10 years of quantum computation, where it's still very theoretical. And I think that the next stage is to understand, is it possible to take the idea of interactive proofs coming from theoretical computer science and borrow it into physics and really design experiments in a new way in existing physical systems, and maybe that will enhance our ability to do experiments in ways that we don't know how to do now.
Yeah, and in fact, there's now I should mention that there are projects underway to try to actually make this transition to with computer scientists and physicists working together on designing such experiments in small, in the small for exactly this kind of thing. Let me make a transition to some questions from the audience. The first of these actually touches upon something quite topical. There was recently in the news, I think many of you may have read about the Chinese launch of a satellite that created these entanglement across several hundred miles, on the ground. So the question says, what are the challenges and opportunities in entanglement for long-distance communication? I wonder if I don't know if do you have anything to say about that experiment? And
I don't have any particular insight except what I read. My understanding is just to try to make long-distance quantum communication possible. I think it's mainly really focused on the cryptographic purposes.
Yeah.
So I'm not sure what's the scientific implication in other aspects.
Actually, while we're on that subject, you talked about how computer science departments have not really taken up the challenge of quantum computing. Is the story different outside the US, and if so, how?
Yeah, I think that in China, at least in regard to the question of quantum computing, I think the computer science department are much more open of hiring people. I think that it has to do with the peculiar cultural setup, namely that because quantum computing and previously quantum communication, they have become the subject of massive funding. So all the universities would like to have a piece of it. And so therefore, I know that that in one of the good universities in China, they hired a computer scientist to be the chairman, to be the dean of their computing school. And one of the first idea that he has is that he wants to establish a department of quantum computing. So I don't know whether he would push ahead and go through the bureaucratic hurdles, but I think that's a very creative idea. And also, I think that in China, that if you work in quantum computing, you have a very big market, both in terms of the academic departments and actually in the industries. In particular, Baidu, I think that inspired by Google, perhaps, that not Baidu, that Alibaba and actually Tencent also, which is another really huge internet company. That Alibaba in particular, they have hired one of my former students, Yao Yuanxi, to start a quantum lab in the Alibaba setup. So I think outside of the US, especially in China, I think they are pretty eager to compete in this arena because this is a good way, a good entry point to establish an international presence in a technology which I really believe is the technology that's going to have billions of dollars of commercial interest in stake. And really, I really don't think that building a scalable, a quantum computer that can handle thousands of qubits is really the biggest prize. I really think that the real goal is to, because of the difficulty, the sophistication needed in building quantum computers, I think one cannot help in the process acquiring a real quantum technology supremacy, which would really be really fire the next industrial revolution.
So I guess,
Yeah, I want to refer to what Andy said about in China there's more openness, and in the US maybe we are missing the boat. And I think there's a question of so there's a very huge, apparently there's a huge barrier for classical computer scientists to really understand the language that quantum computation requires. And really the question is, how do we educate quantum geeks? Is it possible to educate quantum geeks? And I think that the barrier should not be that high, because it seems to me like if there's one course in the curriculum of BSc, we will start seeing quantum geeks very soon.
So I guess there's a bit of a chicken and egg problem there, though, because until computer science departments hire, in this area, you won't get that one course. I should say that it's not just China. Even our neighbor to the north, Canada has a pretty flourishing, programs in quantum computing. Of course, Canada does its own thing, as we know. But
can I add one quick thing? I mean, I have the opportunity to give colloquium and speeches to both the physics community and now the engineering community as people are getting interested. And I really find giving talks to engineers and engineering colleges to be almost more interesting at this point, because they get the idea of building a system and trying to make it useful and pushing it in that direction. And I kind of have a feeling that the future is going to be more in the engineering department. Because physics and engineering have to work together, and like at UCSB, that's really natural to do. But I kind of think in the future, it's going to be in the engineering kind of places where this is going to develop in an interesting way, just based on my interactions with people.
So actually, that gets us to this next question. It's from Dana Scott. Will quantum computers change programming languages, and how?
So I just wanted to follow up on the previous one, then I'll answer that one. We have actually started to talking to some professors that are using our thing to help teach their class. So I think as students get to try things on real things and feel that it's more present, they'll get more interested. Sure. I think long-term a programming language, when we have fault tolerance, is going to be much different to a programming language to get the most out of our near-term devices. So we are trying to start by defining what is the minimalist set that we can give to someone without them needing to know that it's a superconducting system. And so I think at the moment it's just going to go into another language and just be almost like an intermediate representation, not a full language. When we have fault tolerance and we have that all working with error correction close to the device, I'm not sure what the language will be like.
Any other thoughts? I guess one way to address this question, at least to some extent, is the way we think of a quantum computer today is it's a quantum device which is controlled by a classical computer, which provides the puts forth the commands to execute various gates. And so the programming language would sit inside this classical control of this quantum device. And of course, at a low level, you could say, well, then you're just issuing this sequence of gate instructions. But of course, the question really here is, what's the high-level language look like? And I think the answer is, well, there are various people who've been trying to come up with quantum programming languages, but we really don't yet understand what are the things that are going to be most important. So we're really waiting for this.
And just an example, I talked about that we have 3 different qubits. What's the programming language for all of them? But in thinking about the circuit model, we have something with gates where there's distinct gates, but we're also making chips where you kind of have continuous control, and there's some really powerful things you can do with that. So how do you write a language that can encompass both of those kind of ideas? It's something where you have to think about and work on.
So would we say that, as far as the question went, will quantum computers change programming languages? Are we agreed that the answer is yes, we just don't know how, or is that?
I think yes, and we have to build to it, but there's got to how you abstract an algorithm at the highest level, as you brought up with perfect qubits. So there's a lot of work to be done for that.
The other thing, I think Jay mentioned this, is I think we're hoping to do this these languages in an open source environment, so that it's kind of agnostic to the hardware, and then people can kind of develop that as a community. And then of course, as the hardware builders, we have to learn how to compile it to our machine. We're hoping that would be a good model to make it easier for people to do that. And hopefully the community will come upon some standard language that everyone agrees with is good and we can all use.
Yeah, but it seems like really what we need is to see a much larger set of algorithms that we will be using. So for now, the quantum Fourier transform would be a procedure, subroutine in this language, but probably in algorithmic measurements, we will need another procedure, and quantum error correction will need another procedure. We just, I think we need to see far ahead in order to develop such a language.
So we have I think this has got to be the last question, not just because of the time, but because of what it says. So the question is, what do you think Feynman would advise us to do at this point?
Keep going.
I missed the question.
What do you think Feynman would advise us to do at this point?
I think he would have a really good time to see where it's developed. And, his vision was to do quantum simulation. And we're beginning to do really interesting experiments that get very kind of deep information and accurate information about what's going on in these simulators. So I think he would love it because we're just beginning to do those kind of things and see that. And, there's been developments in quantum chemistry algorithm And again, that's really exciting that we might be able to do exactly what he proposed. So yeah, he would love it right now.
Yeah, I don't think he would advise us. He would just jump in and have a blast.
Or if he advised us, he'd advise us to keep playing and to take a break,
Yeah, exactly.
which let's do.